in x equals 1? Like, I feel like we can
Depends.
just put a
It
breakpoint
depends.
on the.
Yeah, it depends on the IDE. In some IDEs, yes, because you can't set a breakpoint here in some IDEs. Maybe this one will let us, but in certain other ones, you can't. This one, it let us do it. So yeah, we didn't need this here. But in something like in BlueJ, you have to put something dumb there because you can't actually put a breakpoint on that line.
Okay.
So
And
just
then,
depends on your IDE. Yeah.
yeah, and then I noticed a warning in the binary search tree. I was curious what that was.
It's talking about null. It's talking about needing a not null. It's yeah, it's
I
there.
no, I don't think it's that. I think it's, or maybe that is.
No, it's a not null thing.
Oh, okay.
Yeah. They don't like the way that nulls work and they want to fix stuff up. So you can try to let it, if you do this, it'll change the access modifier. You might be able to do something else, but yeah, we don't care. Yeah.
Yeah.
Okay. All right. What else, folks? What else about this code? And let me show you just, well, first let me pause a minute and let you ask questions. What would you like to talk about regarding this code? Anything that you want to ask about? How it works, why we wrote X thing, anything you want to ask about that to help you understand it?
Can we go over why we wrote the start node dot left and start node dot right? Yeah, right. No, on the left side of it. What? So yeah, why do we reassign at the end again? Is it the pointer issue that we were talking about yesterday?
Right, because remember the place that you know, if you're, let's say you're adding 1, right? The only time you know where the 1's supposed to go is because you actually went from the 3 to its left. That means you're on now a null reference, right? So the way that you know that that's where it went is that you had ended up with a null reference. But you're now too far gone. You're not on the 3 anymore, you're on the null. So how are you going to make this connection where you take 3 and you make its left pointer point to the null? Because you're already past the 3, right? So the only way you can do that is when you change start node, which is changing the local copy, right? The local thing, you say, hey, I made a new node and I pointed to that node, but that doesn't fix the three's version of that, right? So what you have to do is from the add operation, you have to return this reference and 3 has to store that reference in its left pointer or wherever it was, right? Whatever it was, it has to store that because a new node was added here. And it has to know about that node or else the tree hasn't really added a node. So this is the 3 adding, right? The 3's left is going to be adding the reference to the newly created node.
Cool. Yeah.
Make sense?
Puts it right into the tree where you need it.
But it has to be returned and then it has to be taken advantage of, right? So this thing always returns something and you better store the thing that was returned or else you're losing a node somewhere, right? Here we did it to the root because we started at the root and the root might have changed. Here we did it because we went down the left path and the left path might have changed. So this add will return a reference to that and we better grab it.
Cool.
Make sense?
Yep.
All right, anyone else? It's not an easy concept, right? Not a straightforward concept. Anybody else there? So take a look at the difference in the code, right? Here is some pseudocode for the case where you don't do the x equals change x, because notice you have to be tentative. If you're not using x change x, you have to sort of long arm it. You have to say, well, before I take that plunge, I have to check and see if my left child is null. And if it is, then I make the new node and then I point my left child. And then again, before you take that step on the right child, you have to say, well, if my right child is null and that's where it needed to go, then I make the new node and add it to my right child. So you're always doing these special cases because you're tentative and you can't take the step. You're afraid to take the step because then you've gone too far, right? This is what you do if you're not using x equals change x, but look at how much code it is. Now let's look at the other code side by side, right? It's less code and there's less special casing, right? We're not being tentative about walking too far forward into a null situation. We expect to hit the null situation. That's in fact what we're relying on. And then the x equals change x lets us take care of the situation right, but with less code and less special casing, less tentativeness around those nulls. So literally, like when I was writing this from scratch myself without change x, this is the pseudocode for my code. And then afterwards with x equals change x, this is the result. So a lot tighter code, but there's a lot going on here recursively and with x equals change x. Okay. All right. Any other questions there? That's just the pseudocode. Of course, I'll give you this code, and your author has plenty of code to give you too, right? Your author is going to use x equals change x here as well. Okay. Any other questions there before we move on to contains then? All right. Let's go see. Let's do this first as an exercise of our understanding, and then we'll write the code for this. I want to ask the tree whether it contains the following numbers. Let's start with this one. Let's start with 3. Okay, so if I have to start from the root. So how do I do this? What's my algorithm got to look like? Start at the root. Now what?
It checks if it's null and it's not, so then it compares it.
That's right. So this node is not null, so I'm not out of room. I'm still going. So I found a real thing. I see that it's 8, so it must go to the left of 8. Okay. Then I go to the left and I see that this thing is not null, so I'm not done yet. And in fact, this is the thing I was looking for, right? So I found my answer, and I can now return all the way back up the chain. I don't need to recurse anymore, right? We're going to have a couple of base cases. In one base case is I found it, right? If you find it, you're done. You can just return. You don't have to go searching anymore. But now let's look at what happens if you're adding 2, and let's see if there's another base case. Okay, so again, start at the root, come to the 8. It's not null. We need to go to the left. The left is not null. We need to go to the left. The left is null. So now what? Are we making new nodes for contains?
So just return false.
You return false. But in this case, when you ran out of road, you know it can't exist because you would have found it, right? You know exactly whether to go left or right to try to find it. It's not here, right? If I run off the road into the ditch now, return false. Okay, does that make sense? So in this case, do you see that we've got 2 base cases? The 2 base cases are it's null, so it's not here, or I found it, so that means return true. Otherwise, I know where to keep searching, right? So if we're looking for 9, for instance, right? You go down here, this isn't null, it's bigger than 8. You go down to here, the right isn't null, it's 11, it goes to the left. Then you find it, here we go, we finally found it, right? So it's either I found it, it's null, so I know it's not in the tree at all, or keep searching in the right direction, okay? Take the right path, okay? The other thing I want you to see is, let's take the worst case possibility. Let's look for a number that doesn't exist down the longest path of the tree. 19, start at the top. Not null, goes to the right. The right's not null, goes to the right. Right's not null, goes to the right. The right is null, so it's not here. How many times, how many searches, how many comparisons did we have to do? 1, 2, 3, 4, right? We had to do 4 searches. What's the greatest number of searches that I could possibly have to do in this tree to find whether a number is or isn't there? Height plus the height. In this case, it's height plus 1. The height here is actually only 2, but the idea is, yeah. Okay. The height of the tree is 2. You don't have to do more than that plus 1 or so more comparisons. The cool thing is you can have a tree, and let's talk about the math. Let's say that you have a tree that is height balanced, right? Has to be height balanced. And let's say that it contains 1,000 elements, right? 1,000 elements. If the tree is height balanced, what's the greatest number of searches that you're going to have to do roughly? Anybody know the math?
It's log of 1,000 base 2, right?
Right. So 2 to the what power gets you closest to 100 or 1,000? Nobody knows their powers of 2 that far? 2 to the 10th is 1024. The most searches, again, it's like plus 1 or so, that's fine, we don't care. More or less, that's 2 to the 10th. That means 10 searches will let you find something in a tree that's got 1,000 items, right? It's a very efficient thing, right? In fact, we would describe this as big O, and we'll come back and talk about that, big O of log n, right? Big O of log n. As n gets bigger, as the number of data items gets bigger, the search time gets bigger much more slowly, okay? So for 1,000 items, it takes 10. For 1,000,000 items, we're only up to 20 or something, right? It doesn't get big very fast. This is a very efficient search mechanism, right? Does everybody see that? But it's based on the tree being height balanced. If the tree's all wonky, then it's a different matter, right? The tree has to be height balanced to maintain this kind of performance, but it's good performance, right? No linear search here, right? This is a pretty darn good thing. We'll talk more about performance and complexity, but that's the idea here, okay? So now let's see if we can go encode that, right? Can we take that idea and can we write the contains method using everything that we've done so far? All right, so let's say we want public, in this case, it's going to be Boolean contains. You're going to have to give me some data, which is the search data, and it's going to be an int. Again, public front end for these things typically, and that's going to call the recursive one, and that's going to call, return contains, and we're going to pass along the search data, and we're going to start at the root, right? And then we know that the private one is going to be very similar to this, except it's going to have binary int tree node, binary int tree node. Why is that not working? What am I misspelling? And I need start node. There we go. Okay. Again, public front end and private recursive function. The first one's always going to kick it off by calling that private recursive function with the root, because we got to start there. Now, how do we write our code now? Using everything we just learned, what are our two base cases?
If the start node is null.
If the start node's null,